So in today's class, we are going to I am going to give you a brief introduction about a deep sub-micron MOSFET operation. Okay. First let's just revise what we learned in our VLSI classes, the normal long channel MOSFET operation. Okay, and then we will try what is the we'll try and understand what is the difference when the channel length is comes into the submicron or deep submicron region, and how the current characteristics and the MOSFET operation gets modified. So let's just take a quick review of how MOSFET operates in the long channel, okay, the normal MOSFET operation. Okay, so if you see here an N channel, how is an N channel made? You have an P substrate, and then you cut open two windows, and then you do implantation of an end dopants. Okay, so you have a source region and a drain region out here, and between these two regions you have something known as channel, which is intrinsic P itself. So this P is an intrinsic. Actually, the doping concentrations generally for this is around 10 to the power of 15, right? Okay, then you have an insulator, which is generally silicon dioxide in the earlier days, but as the technology has advanced and the device sizes being shrunk, so you have once you are shrinking the device sizes to, so the oxide thickness also needs to be accordingly reduced. Okay, so what happens is for very low technologies like 45 nanometer and all, the oxide thickness becomes very thin, so they become unreliable, so they can get punctured, right? So instead of using silicon dioxide, these days we use hafnium dioxide or high K electric, which has got the same electrical characteristics. It has got high K. Say HFO2 has almost 4 times K of silicon dioxide. So instead of using, I am just giving an example, a 1 nanometer silicon dioxide, I can use a 4 nanometer HFO2. Both will have the same electrical characteristics, but then using 4 nanometer will prevent leakage currents from the gate side. Okay, so that is a gate oxide out here, and over that we have a gate. Earlier days we used to have a polysilicon gate. These days we have other metals like molybdenum and TiO2 and things like that, so that another VTH can be accordingly set, okay, for the low channels, because there is a requirement to bring down the VTH also as we are scaling down the devices. So polysilicon, instead of polysilicon, if you use other metals, so we can, that is known as gate engineering. We'll see that also today. Okay, so when you don't apply any gate voltage, so this is something, this figure shows how the channel looks like. So it is just going to remain in a pure intrinsic or a lightly doped P material out here. So this can be, if you apply a positive voltage either on the source or the drain, so one of these junctions will be reverse bias. So this can be shown as an equivalent two diodes, back to back connected diodes here, right, with N here, when N here, P in between. So this is how this looks like. So when you apply without any gate voltage, if you apply a potential between drain and source, one of these diodes will be reverse biased, and hence the current will be 0. Okay, practically it will be few picoamperes, but then we can assume that there will be no current flowing in this when you don't apply any gate voltage. Okay, so this is how a MOSFET operates in a normal MOSFET operates. Okay, now if you try to derive the equation, so we know something known as threshold voltage. First we have to know what a threshold voltage is. Okay, now what is a threshold voltage? Let's try and define. Okay, threshold voltage is that voltage for which, okay, now how does a MOSFET operates actually when we apply a gate voltage? What happens? Okay, the first thing which happens is once you apply a positive voltage here, the positive carriers which are available out here they will be repelled back from the channel towards the substrate, because you have applied a positive potential here. So first thing is, all the positive ions will be repelled from here. Okay, so and then it is known as a depletion layer here, so it will be devoid of any carriers. So that is the first thing which is going to happen. In the second step, as you keep increasing the voltage, then there will be electrons which will be pulled into the channel region because of the positive potential which is applied here. So those electrons can come from the source, drain, and from the substrate. Okay, because this is N, and also from the bulk also some electrons, whichever is thermally excited electrons, they will come and they will form a channel out here, right? And threshold voltage is that voltage for which the concentration of electrons is equal to that of the holes with in the bulk region out here, right? So initially, suppose here what if P is doped with 10 to the power of 15 per centimeter cube. Okay, now when we apply just the threshold voltage, the concentration of electrons out here will be 10 to the power of 15 per centimeter cube. Okay, so it is defined like that. Okay, the threshold voltage when the surface is supposed to be inverted. Now, inverted means the density of the mobile electrons on the surface becomes equal to the density of the holes in the bulk P type. Okay, so whatever is the doping here, equal doping will be equal number of carrier density will be here of opposite polarity. So that is defined as a threshold voltage. And when the voltage applied here is more than the threshold voltage, we assume that a channel has been formed, and now depending on the potential which is applied across the source and the drain, a current would flow from the drain to source or source to drain, depending on the polarity. Okay, so this is what an threshold voltage is. Okay. Now the threshold voltage has got four components. Okay, so the first one is known as the work function difference between the gate and the channel. Okay, so when you are applying a gate potential out here, right? So what happens is there will be a lot of free electrons available in the metal, because metal has gotten a great work function. In the metal you find the electrons are more free to move around, right? So what happens is because of more electron density out there is the electrons out here to we'll have to do that bit of extra effort to pull the electrons out here, right? Because once you have placed a metal, you have placed an insulator, and there is an P type substrate here. Okay, a potential will be developed out here. Okay, inbuilt potential even without doing anything, because there is a metal out here, and there is an because the work required work function, there is a work function difference, and because of which there will be an potential which will be developed across this junction. So you will have to overcome that potential difference to create a channel here. Okay, so that also becomes a component of the threshold voltage. So that is given as a work function of substrate minus F metal for metal gate, or F polysilicon for polysilicon gate. So your threshold voltage, whatever you apply, has to overcome this particular work function. Okay, which is given out here. So this is the formula. Now 5 GCs, 5 substrate minus metal, substrate minus. Okay, why is this greater? This is the quantity of work required for pulling an electron from the substrate to the free channel, right? So that will be greater, whereas this is the work required for pulling an electron to the free space. So obviously you will require more work for pulling an from, because this is slightly doped. So from the substrate it is more work requires to be done, whereas to pull an electron into free space lesser work will be required out here. Okay, so that is why 5 GC comes as a positive value out here. Okay, which so you will have to, so this adds a positive component to the VTO. Okay, so if I physically think, and I can say that since there are a lot of free electrons already available here, so they are going to repel the electrons from here into this channel. So but I require electrons here for this to start conducting. So I'll have to overcome that particular ripple. I'm trying to explain it in a layman's language. Okay, so I have to overcome this particular component to create a channel out here. Now what is one takeaway from here is like the threshold voltage, okay, depends on the kind of metals which we are using out here. So earlier days it was polysilicon, but as the technology when we are moving from say 180 to 90 to 45 to 22, what is happening is now it is like we are going to learn that today in the second part of the class. We are doing constant voltage scaling, that is we are shrinking the device size, but we are going to also reduce the VDD also by the same factor, so that the electric fields are kept constant. So if you don't keep the electric field constants, okay, if you just reduce the size of the device, then there is a possibility that there will be a high electric fields will be set, and that will damage the device, right? So electric field is what? Voltage divided by length, right? So if you reduce the length and if you keep the voltage constant, electric fields will keep going high, and that will damage the device. So you need to scale down the VDD also. So now if you scale down the VDD, okay, you can't keep VTH same, right? So you will have to reduce VTH, because we saw in our first class, if you know for current, and we'll see in today's class also, in the current equation, VT greater VT means lesser current. So to keep the currents constant, I need to reduce VT. So one way of doing that is, instead it is known as gate engineering, where we are going to use a different appropriate metal, so that we have a lesser VT out here. So if you see generally for 45 nanometer technology, you have an for the PMOS, right, you have an N substrate and molybdenum is used, and I think TIN or TiO2, I'm not very, I don't remember correctly, but some alloy of titanium is used for NMOS. Okay, so you can just do a quick Google search and you will find what are the different metals which are used for various technologies. Okay, that is essentially to tune the VTO to the desired value. Okay, so that this component comes from there, and then you have another component which is known as 2πf. Okay, what is this? This is the quantity of voltage required to invert the channel, right? So we defined VT as the voltage required for this to get inverted. That means whatever was the initial concentration in the bulk region, the opposite charges also in the channel should have the equal number of it should have the same concentration levels, right? So if you see here, so that can be given by this equation. It is 5p kT by q ln Ni by Na. Okay, Na is the concentration of the dopant in the substrate. Okay, Ni is that intrinsic Ni. We know it is 10 to the power of 10, right? So you have Na out here. So this gives the value for 2πf, right? So now if you see here, here also again the takeaway again here is like when we are if you increase Na, okay, Na is in the denominator out here, right? So it will become more negative. So it will be negative out here. So this negative gets cancelled out here, right? So you have to. So if you increase Na, right, the threshold voltage increases out here, right? So but if you decrease Na, right, and so what happens if you decrease Na, then the threshold voltage decreases. Okay, so now there is a trade-off out here. So if you reduce the if you want to reduce VTO, right, if you have to reduce the VTO, you can decrease the concentration of this bulk region, right? Because now all that we are going to do is we have to make these two the concentration of the new carriers to be equivalent to that of the poor. Just one second. Yeah, okay. So what I was saying is, if you increase the concentration, bulk concentration out here, right, the threshold voltage will increase, right? And if you decrease the threshold concentration out here of the bulk region in A, the threshold voltage will decrease. Okay. So if you try to reduce VTO, you will find that now you can decrease the concentration, reduce the VTO, but what would happen is the static leakage currents will increase, because if you see here in the first here these diodes they will become weak, right? Because this is an, if you decrease the concentration of the p type, so these reverse bias junctions they will become very weak if p is very lightly doped, right? So that is the reason. So there is a trade off between the VTH and the leakage currents. Okay. Then again you have one more component, which is CBO by COX. Okay. What is BO? Now when you are pushing the holes out here, a depletion layer will be created out there, right? So this is just a revision. You can go through your VLSI classes notes. You'll recall the detailed derivations. Okay. What is QBO? A depletion layer will be created, right? When you are applying a voltage here, so that will act like a parallel plate capacitor, right? There will be a conducting layer, then there will be a depletion layer, and then there will be a substrate. Because when you are pushing when the holes move out, right, there will be a small depletion layer which will be devoid of any charges. So that will act like an insulator. Okay. So this becomes like an conducting layer, an insulator, and then again a conducting layer. So that becomes like an capacitor. So you will have to overcome that effort also. So it is QBO by COX. Okay. Although there is a negative sign out here, right? Here there is a negative. So you will have to. So this ultimately this becomes positive. So these they are going to contribute towards an increase in VTO. Actually, these three components. Okay. This negative comes, that gets cancelled because NA the concentration out here. Okay, the dopant concentration will be more than Ni intrinsic. So this will become automatically, there will become a negative, and negative this will become positive. Similarly, here there is a negative out here and this negative. So you will have, because the capacitance has been formed here, you have to overcome that capacitance also to create a channel here. So this also is an actually it will be it will create a net positive effect on VTO, right? And finally, you have sir, the Fermi metal of yeah, correct. So because see that is the work required to take the electrons from the to a free space. So you will require more work to take an electron, because they are not that free. So you will require more work to take an electron from the substrate to a free space, for it to participate in conducting. Whereas in the metal, with a little bit of work only, the electrons are available for conduction. So this is less. So this again 5 GC is and it comes out to be positive out here. Okay. Okay. I was talking about this. Okay. Now while fabrication, so there will be some discontinuities in the layer which is formed, and some impurities gets trapped in the interfaces also. So this is because this is not a controllable thing. So you will have to cater for the threshold voltage depends. So these things are fixed, like controllable, whereas this is because of the process which comes in. So you will have to cater for that. So this could be negative, positive. Generally it is a positive. Okay. QOX. Okay. QOX is positive. So this results in a decrease in VTO, because there will be some positive charges which gets trapped in the interfaces. Okay. But you can also intentionally trap some particles if you want to modulate the VTO. Okay. So that also can be done. So that also comes out in this particular term. Okay. So this is how a threshold voltage looks like for a MOSFET. Okay. And also you might have done this derivation in your VLSI classes, where the threshold voltage gets modified. So till now we were talking about the substrate being grounded, but in a VLSI circuit sometimes the circuit the substrate the source being grounded. Sometimes the source cannot be grounded, because like for example in an AND gate, one MOSFET is placed over the other, so this source is getting connected to the drain of the next transistor, right? So and if this transistor is on, the below transistor is off, there is a possibility that there will be higher potential out here, okay, on the source. So in those cases the threshold voltage gets modified. So you could think you can just try to relate it like whenever a gate potential is applied out here, extra voltage is applied out here, you can assume that this is negative, this is ground, and a negative voltage is applied out here, okay. Instead of thinking it this way, that this is at a positive voltage, we could also look at this way, that this is ground and a negative voltage is applied out here, okay. Now if I consider this MOSFET as a double gate structure, if I am giving a negative voltage out here, then it is like opposing the positive voltage which is applied on the front gate, okay. So it is a double gate structure now if you consider it that way. So since you are giving a negative voltage out here, the threshold voltage will tend to go high. So now this threshold voltage equation is modified out by this equation, where you find VSB. Okay, VSB is nothing but the source to body voltage. Okay, so if we consider the source to body voltage, so the threshold voltage gets modified like this. Okay, now the threshold voltage VTO is the threshold voltage without body bias, and this is the total threshold voltage considering the body bias also. So this is how a threshold voltage of MOSFET. Okay, this is just a quick revision of what we did in our VLSI classes. Okay, now if we try to derive the MOSFET and current equations, we will first try and see how the current equations in a normal MOSFET looks like, and then we will see how it is going to get modified because of the various short channel effects. Okay, so if you see here, when we apply a small VT, okay, to the channel out here, so we are assuming channel is formed out here, right? So this is, we have applied a voltage which is greater than the threshold voltage, okay, which is given by VOV VGS minus VT. Okay, this is the overdrive voltage which we are giving out here, right? Now if you see here, this is the voltage, and if you consider this as the gate capacitance COX, the charge which gets accumulated in the channel will be like C into V, right? Charge is Q is C into V, right? And COX is the capacitance per unit area. No, COX, oxide capacitance, is per unit area. So you need to multiply it with the W in and L, and this is the V over V overdrive. Okay. Now V overdrive, we are removing this VT because the portion of the VGS, okay, a portion of the VGS will be utilized to create the channel. So that much voltage is not available to us. Okay, only the voltage which above the VGS is available with us for creating the extra charge out here. So that is why we are taking VGS minus VT out here. So this becomes out here, right? So charge per unit length is Q divided by L. It will be COX V W V over drive. Okay, so this we get one equation out here. And then also, what is the electric field? Electric field is VDS by L, right? So we are applying a drain voltage here. This is the source voltage. So electric field will be set across here, which will be VDS divided by L. Okay, so velocity is of an electron. Okay, here in this case it is electron. So mu n. Okay, it will be given by mu n into E. E is the electric field. Now for E I substitute this, so I get this value. Okay, mu n E is equal to this. Okay, now the current is a velocity into charges per unit length. Okay, so that will be the total current ID. Okay, V into Q by L. So Q by L we already found out here, and the velocity is again given by this equation. So if I substitute these values, I get an ID equation like this. Okay, now if I see this ID equation, it is mu n Cx W VGS minus VT by VDS. Okay, so for a fixed VGS, okay, with VDS the current increases linearly. So for a small VDS, I can say this is going to be the characteristics. Okay, so for a small VDS, the current is going to increase linearly with VDS. So it can be used as an what variable resistance. Okay, and how to change the value of the resistance? By changing VGS. Okay, so for analog applications and all, where you can bias this transistor in the small VDS regions, right, and then modulate the resistance by using a bias at VGS. Okay, so this is for a small VGS. Okay, you can't, the equation gets modified when the VGS for when the VDS increases. Okay, for a small VDS, sorry, for small VDS. So for the small VDS, you can consider, you can use this MOSFET as a variable resistance also. Now generally a lot of you get confused with these notations. Now K prime N is mu n Cox. Okay, just remember that. Okay, and Kn is mu n Cox into W by L. Okay, so if I include this Kn and Kn is mu n Cox, so mu n Cox W by L will become Kn. K prime doesn't cater for W by L. Okay, so this is Kn dash. So this notation you have to be clear. Okay, so in numericals especially, many of you go wrong. So just be careful with this notation which is given out here. Okay, now as we slowly increase VDS, what happens is the channel gets tapered out here. Initially it was a rectangular out here. Right now, because of the VDS, okay, now this junction also starts getting reverse bias. So there will be some depletion which is because right, this is P and this is N, and you are applying on a higher VDS. So this slowly this depletion layer will start forming. This is known as the channel. So the channel gets tapered. So for again, so now this current equation out here, because the entire channel is not available out here. So if you see here, because it is tapered and the charge is proportional to the cross sectional area, this equation gets modified out here. Okay, the difference out here from here to here is, here we had the full VOV, and now we are having a VOV minus VDS by 2 into VDS. Okay, obviously the currents will be larger out here as compared to here. Okay, currents will be larger because now this is very small VDS. Here it is a large VDS. Okay, but you have VOV minus VDS by 2 out here. Okay, so now this is the new current equation. Again, this is considered to be in the linear region. So in the linear region, so the condition for a linear region is again VDS is less than V overdrive. Okay, VDS is less than V overdrive. So that is the condition for linear region operation. Okay, so this is the equation now. So if it is in linear region, we need to use this equation out here, right? And we further, if we keep increasing the VDS, okay, this channel will ultimately get fully pinched off. Okay, because the depletion layer, because of this reverse bias, and this channel will get totally pinched off. Okay, and further increase of current won't be possible out here. Okay, the current will get saturated. So that is known as the saturation region. So in the saturation region now out here, okay, VDS is equal to V overdrive. Okay, so because then there is no more threshold voltage difference available between the gate and the source and the drain and the source. Okay, so that gets pinched off out here. Okay, so if you see here now, what is the pinch off? Where the drain, so the voltage between the drain and the gate is equivalent to threshold voltage. So if you see, if you substitute that out here, you will get VDS is equal to VOV. Okay, so that is the over VGS minus VT. When VDS reaches that particular value, this channel will get pinched off here. Okay, now if you substitute this as VOV, okay, you will get VOV minus VOV by 2, you will get VOV by 2 out here. So this 2 comes out here in the denominator out here, right? And then this becomes an VOV, right? This becomes VOV. VDS is also VOV. So you get VOV in a square, overdrive square, and what is V overdrive? VGS minus VT. So VGS minus VT square. So this is the new equation now in the saturation region. Okay. So now if you see here, there is no VDS component out here, and that means once it is got saturated, then any further increase in VDS will not yield higher currents. Okay. Now because the channel has got pinched out here. So here this becomes independent of VDS, and the current levels will be only be decided by the VGS factor out here, right? So this is the new current equation. So this is how the response looks like. So if you keep increasing VDS in the above the VDS sat value, which is given by VGS minus VTN, there won't be any. This will remain kind of horizontal. Okay, so you can only increase the values of the current by increasing VGS. Okay, so this is what the current equation in the saturation region. So even from your examination point of view, all these equations you need to remember for all these three operating regions. Okay. Okay. Now we have something known as MOSFET and body connection. Okay. So what if you see here, these substrates are there, right? So for an NMOSFET, okay, the body needs to be kept at the lowermost potential which is available in the circuit, to ensure that this P and N, okay, is reverse biased. Okay, so you will find there will be source and drains which are of N type. When the channel, why does the current current doesn't stop out here, because see, the current has increased, and if the current stops, again the channel will start getting so it is an equilibrium position. If the current stops, then the channel will start increasing. Okay, and then again, so it's an equilibrium state actually which has been received formed out here. Okay, so that is the reason. So if you see the body out here, the body is body needs to be placed in the lowermost potential out here. Okay, why it's placed in the lowermost potential? Because to ensure that the source and the drains, the N regions, with respect to the P, they are reverse biased. Okay, otherwise what happens is, if there is a positive potential available on the body, and then you have a source and drain to be lower than that potential, then this diode can become a forward bias, and that will fail this MOSFET operation, right? So you can't have that. So you have to always, all the body of all the of the NMOS will be connected to the lowest possible potential of the circuit. Similarly, for an PMOS, if you see, it will be a N substrate, and to ensure that this diodes formed by the drain and the body, okay, to be in reverse bias, you have to keep the body at the highest possible potential. So generally NMOS you give ground, and PMOS you give VDD out here. But if you see an NMOS out here, so this is another mistake which we generally do in the schematics. If you have an NAND gate like this, okay, we try to do this shorting between the body and the source. Okay, so you can't do that for this particular. Okay, you have to separately pull the ground for each of these transistors. Okay, the reason is here, like you have two NMOS placed out here. Okay, this is body is ground. Okay, the bottom one, it is grounded out here. Suppose and here for the bottom you can put since this source is also grounded, you can make a short out here. But here if you make a short, what happens is, suppose this PMOS is switched on, this NMOS is switched on, and this is switched off, right? For A is equal to 1, B is equal to 0. Then the voltage out available in the source here will be VDD. Here it will be VDD. But if you short this out here, it will be VDD out here. But here it is ground. So you find here VDD is getting shorted to the substrate out here. So you have to be VDD getting connected to ground. Okay, so you understand what is the problem, right? So you should not do that. So whenever you are making these kind of circuits, ensure that and in the schematic, okay, all the obviously in the layout, so you will take care of that. In the schematic also, you have to take care that all the body connections are separately connected to the ground, and you are not just making the source and body short everywhere in the schematic. Okay, and the same holds good for the PMOS also. So whenever you are making PMOS circuits out here, you have to ensure that the body is connected to VDD independently. Here on the for the topmost, it is okay, body to source short, this is okay. You can't do it here, okay, because again it would happen if you are connecting an VDD out here. So there is a possibility that this source or this drain can be ground. If this is switched on out here and these are switched on, so this will be 0 out here and this will also be 0 out here, right? So if you connect, if you do a short here, so there can be VDD to ground and a connection. This can form like that. So you have to, for these when you have different PMOS in the circuits, each of the body should be separately connected to the highest potential available in the circuit, which is generally the VDD. So you got to take care of these things also, right? But in certain if there is a requirement of using a separate body, so you have a P substrate, you can have a deep when this is known as double well, in which you have an this is not an this is one more N well, and then you have this P well. So this is not a global P well. Okay, so here you can use in fact in certain circuits and in certain circuits such kind of devices are also used, where you can modulate the threshold voltage by giving an separate voltage to the body out here, right? You have where low VTs are required in certain applications like RF rectifiers and all. So these kind of things are also can be done. Okay, now this is not a global substrate, right? It is a local substrate which has been formed here. So now this body is independent. So you can give a positive voltage out here also. Okay, to modulate VTH. Generally, it is done for those purpose. Okay, so you can do that also. This is another thing which we need to take care. Now suppose you have an NMOS and a PMOS which is placed close to each other. Now if you see here, this is a P region, this is an N region, and this is the N well of the PMOS. So this becomes an NPN transistor out here. Similarly, this is an N, this is an P, okay, of the P of the substrate out here, in which the NMOS are fabricated, and then you have another P from here, right, which is connected to VDD. So there will be some in the bulk region, there will be some resistances, right? So they are represented as RP and an RN. So if I make an equivalent circuit, it looks like this. Okay, so what happens is, suppose a small leakage current flows here. Okay, what happens is, this is small leakage current flows out here. This voltage will drop here because of this RN. So this is an PNP transistor. A low voltage dropping here will increase the bias across the base emitter, right here. So more current will flow here. That higher current will again flow through RP, and it will increase the potential here. This increase in voltage will again increase the current here. So you see a positive feedback network has been formed here. A small leakage current here, a current here will result in a voltage drop here. A voltage drop here will increase the current here. That will increase the voltage out here. That will further increase the current here. So now you can have a condition where it's a positive latch, and you can have you can land up into a situation where an high current is flowing between a VDD and ground. So to avoid such things, generally you place an extra N guard, okay, over your you have in this region, you have your entire PMOS of your circuit, and then and then you on this region you have your entire MOSFETs of your circuit. Then you put an extra N plus guard ring, or you can put an and then you also place an extra P plus guard ring around your MOSFETs. Okay, so that is to avoid the latch. Or you could have an trench isolations also. Okay, so this is silicon dioxide. This is shallow trenches, and these are the deep trenches. So between your NMOSs and the PMOS devices, so you can have a trench isolations also to prevent a latch. Okay, so now this was just the revision of what we did in our VLSI classes. And now coming to deep submicron MOSFET operation. So let's first define what is submicron and deep submicron. So if you see here, anything from 300 nanometer below, you could call it as a deep submicron. Okay, channel length. This is the channel length. Okay, so this is 0.3 micro, 300 nano. So these are all deep submicron, and ultra ultra deep submicron is anything below 100 nanometer. Okay, so 90 nanometer and 60 nanometer, 45 nanometer, they can be called as deep ultra deep submicron. Okay, and nanotechnology is below 30 nanometer. Okay, so everything like these days what we have 22 nanometer, 7 nanometer and all, they can be classified as nano devices out here, right? So these are the effects which we see in deep submicron MOSFET operations. Threshold voltage reduction, they can be because of two effects, which is VT roll off and drain. We'll see each of them. They could be mobility degradation, velocity saturation effects, channel length modulation, subthreshold conduction, and hot carrier effect. So these are some of the drawbacks or issues which we face in deep submicron MOSFET operation. So we'll briefly look at each one of them. Okay. Now this is known as a VT variation. So this is a long channel device. If you see here, so when you have the source and the drain, this is N and this is P. Obviously, normally when you have an NP type of semiconductors placed close to each other, a depletion layer will be formed. So a depletion layer is nothing but a layer which is devoid of any charges, right? So that is a normal PN junction depletion. So here you have a normal PN junction depletion. Here also you have. But since this channel length is very large compared to the small depletion which forms out here, right? So it doesn't have a great effect, okay, in the long channel devices. Okay, but when you bring the devices close to each other, okay, the source and the drain, because now we are speaking of submicron devices where the source and drains are very close to each other, then you see here this depletion layer, and now you have a continuous depletion layer. Okay, and now obviously, so this is going to result in a decreased VT. Why? Because what was VT? VT was the quantity of work which we required to create the depletion also, right? Now this depletion is already being the depletion is happening because of the source and the drain regions being opposite of opposite polarity than the substrate. So that itself, so this depletion layer is now happening of its own rather than we having to work hard by applying a gate potential. So that reduces the VT. Okay, so that is why. Similarly, you could have a drain-induced barrier lowering, because now the drain is we are giving a positive voltage to the drain, and the substrate is a P type which is ground. So this is the reverse bias junction. So that also increases the depletion layer. So in both of these, VT roll is just because we are getting close to each other, and drain induced is because the higher potential given to the drain. Both of these things, what they are doing is they are creating a depletion layer which otherwise we had to create by giving a gate positive voltage. So that is why some work which we required to do, okay, in terms of applying voltage above VT, so that is being done by these two effects. So VT is slightly reducing. Okay, so this is one of the effects which we see in threshold submicron devices. Okay, and also the next effect is mobility degradation. So why do drain induced, we call it as drain induced, because when we apply higher potential in the drain, okay, a depletion layer will be caused between the drain and the because of this this junction is getting reversed by, so that is why we call it as drain induced. Okay, so now if you see here, normally when we talked about mu n, okay, we let me go back to that slide. Okay, here, right, we mu n e. So this electric field, now how did we define the electric field? VDS by L. So we were assuming that there is a horizontal electric field available out here, right? So that which was accelerating the electrons out here. So we computed the velocity of the electrons by mu n into e. We never in this case we neglected the vertical field which is available out here, right? So that is not a big issue in the because if you see here the device and length here, these lengths are very large, so the electric field will be very weak, right? But now in the sub micron technologies, the here, okay, because of the vertical field also, the mobility of the electrons gets affected. Now mu n effective is again given by a modified formula, mu n, okay, by 1 plus VGS minus VT. That is, if you apply more VGS, it will create a vertical field which will degrade the horizontal mobility. Okay, so higher VGS will degrade the mobility, and this is theta. It is an empirical parameter. Okay, so this will be given by the Fab Lab after doing statistical analysis after experiments. They find out the value of the theta, and that is provided out here. So you will find here this mobility gets degraded because of the VGS voltage out here. So now the mu effective voltage gets modified here in the deep submicron devices. Okay, another thing effect which we can see here is, earlier we said as the voltage increases, the mobility of the electron will keep increase. Okay, will keep increasing linearly. But that doesn't happen in short channel devices, since the electric fields are high out here. So the velocity gets saturated. So the electrons cannot go beyond an particular beyond a certain limit. Okay, so the velocity of the electrons gets saturated. So this is what hence the equation for the velocity now here gets modified by mu n e divided by 1 plus e by ec. Okay, e was the electric field, n was the mobility here. Okay, initially we had v is equal to mu e. Okay, now it gets modified by mu e divided by 1 plus e divided by ec. Okay, so when the electric field is much lower than the critical voltage, this is the ec is the critical voltage. Okay, that means below, if you don't apply this high E is the normal electric field. Okay, VDS divided by L. So when E is much smaller than EC, then okay, this term can be neglected. You can say velocity is mu n E. But as E increases, as you keep increasing in a VDS, it reaches a critical value. Okay, beyond which the velocity doesn't increase. Okay, so this velocity equation gets modified. Okay. E or electric field is in E. Okay, so this is known as an E sat. Okay, E sat. So now if you see here, this is an E sat. Okay, so when E is equal to E sat, V becomes a V sat. Okay, so this equation. So you will find that for an 8 into 10 to the power of 6 centimeter per square for electrons, that is the maximum velocity now it can attain, and for holes it is slightly lesser, 6 into 10 to the power of 6. Okay, so this is what the the equations now accordingly the ID equations also gets modified. So if I see the ID equations now here, this is how it gets modified in the linear region and in the saturation region. So these equations you need to remember for your exam. Okay. So you have W by L and a C aux and a mu effective. Now it is not mu n, it is a mu effective. Okay, and mu effective is given by this formula out here. Okay, so this gets modified, and in the mu effective gets affected and gets modified here like this, right? And also this is because of the velocity saturation. Okay, so this factor comes out here. So this is the modified equations for the linear region and the saturation region for submicron devices. Okay, so you need to most of these values will be given to you. But you need to remember these equations to compute out here. Again, m is also an empirical value which will be given. Okay, so these are the current equations. And now this is what happens, right? So with increase in VDS, because of the velocity saturation, the net effect is the current will not be as expected. Okay, so there will be for short channel devices, there will be a drop in current. Okay, you won't get the current as expected because of the velocity saturation effect. So this is how what happens. This is a plot for a long channel. This is for a short channel. Okay. Another thing which we can observe out here is something known as channel modulation. So after pinch off, and if you still keep increasing VDD, okay, this will keep moving towards here. Okay, so a depletion layer will be formed here. Okay, a depletion layer means there is no free charges available here. Okay, but there is a potential across this depletion layer. So any electron which is available here, that will be pulled by the drain voltage out here. So they'll move through and through. Okay, but what happens is as you keep increasing this voltage, this depletion layer out here keeps moving towards the left out here. Okay, so in effect what happens is the channel length is reduced out here. Now because if you see the ID equation, L is in the denominator, right? So so you will find that what does channel so since there is no free charges available out here, okay, the length is effective length is out is decreasing out here. That means W by L, right? So that is increase. So in fact the current will increase. So if you see here, normally this current has to get saturated, but because of channel length modulation, if you increase VDS, you will find that the current is slightly increasing out here, right? So this is known as the channel modulation effect. Okay, now hence the ID equation for a channel length modulation, okay, it gets modified like this, ID mu n C ox W by L. Now so this equation is again very important from your examination point of view. Okay, so ID is equal to half mu n C ox W by L. This is just we are not here we are not catering for okay these effects. We are just talking about the channel length modulation effect. Okay, so just remember this formula also. Okay, so this is VGS minus VTH 1 plus lambda VDS. Okay, that means there is going to be increase in current with increase in VDS. Okay, so that is being reflected by this additional 1 plus lambda VDS which has been inserted into the ID equation. Okay, now what is this lambda out here? Now if you see these curves are slightly now they are not horizontal with respect to VDS, they are increasing. So if you try to extrapolate that, they will come and meet at a point which is known as an early voltage, and lambda is given by 1 by VA. Okay, so this is what the current equation gets modified with this lambda. So this lambda is the 1 by VA, and that is what is inserted out here, right? So for analog circuits, the output resistance, this is not for digital circuits. Generally, we don't look at this, but for analog circuits, for when we change in a VDS, what is the change in VDS? That will be given by the slope out here, right? So that will be given by 1 by lambda ID. Okay, so this is for the to define the small signal slope out here. This is for analog circuit. So you can. So this formula is used out here, right? And the last concept out here which we are going to discuss in subthreshold is subthreshold conduction. So generally for long channel devices, we assume that if the voltage is below VTH, the current is 0. Okay, but for short channel devices, what happens is, because the threshold voltage is very low now, okay, because the VD is low, like for 180 nanometer VD is 1.8, whereas for an 45 nanometer is just 1 volt, right? So now accordingly the threshold voltage also for it is close to 0.7 threshold voltage for 180 nanometer, whereas for an 45 nanometer it is around 0.45. So if VT is low, then that means even when the voltage is below VT, there will be a lot of current, substantial amount of current. Okay, so that is known as subthreshold leakage currents. Okay, so you will find there is this is, if you see it in the linear scale, it may not be visible, but if you put a log scale here, you will see that there is a current out available here also, from nano to micro range out here, right? So and that current equation is given by this particular formula. So we'll not get into the physics of this. Okay, so you have to understand that when the devices in the short channel devices, okay, there will be a lot of currents in the subthreshold region also. Okay, so the leakage currents are here. If you see here, the leakage current is a few picoamperes. Okay, unlike in long channel devices, it will be of the order of 10 to the power of minus 15. Okay, but these for short channel devices, because of lower VT, the leakage currents are very high. Even if when you give VDS is equal to 0, you will find the leakage current is close to 10 to the power of minus 11. Minus 11 is what? Around 10 picoamperes, right? So even in simulation also, what you have done, I think off currents you might have seen these kind of currents you might have observed. Okay, and then finally we have something known as hot carrier effects. That is because when these electrons are moving from the source to drain at such a high velocity, and you have for the short channel, because devices, some electrons they acquire enough energy and they punch through the oxide layers. Okay, so they get trapped, and because of which the VT of the transistors they get affected. Okay, so they could be long-term reliability issues also. So these are all the problems being faced in the short channel devices. Okay, these conditions below 1 micro devices, these effects are visible. Okay, so this is one more effect. So